All right, so let's look in here. So today we're going to talk about rates of change in linear and quadratic functions. Again, should be some things that look familiar, but we're going to kind of maybe approach it in a little different way than you've seen before. Coming up on our first quiz on Friday. Okay, so this is the last piece of information that'll be on the quiz that you'll take on Friday. The Johnson family loves candy apples. Are y'all candy apple fans? Oh, okay. There's this, I always go to this not craft, but like boutique sale over in Lebanon every Christmas. And there's a lady there with these homemade caramel apples. Yo, it's just not fair how good they are. Okay. But I bought pretzels this time instead of apples, so I wouldn't eat as much. The Johnson family loves them so much that they pay the family price of $8 entry fee for the county fair as often as they can to buy some for the whole family. The apples are $4.25 each. Model this scenario with a linear equation where J of A is a function representing how much money the Johnsons will spend, and A is the amount of apples that they buy. Okay, what do we get for that? So nobody answer at once, it'll scare me. Yep, 4.25A plus 8, okay? 8 being our entry fee, $4.25 per apple, and then J of A, our Y value, or how much we'll pay, okay? So then now let's interpret it in context. What does it mean? What was the slope or the rate of change in this equation? Yeah, 4.25, which just meant for every apple purchased, the cost increased $4.25. Okay. And then that leaves our y-intercept to be 8. All right. And that's just telling me that this is the cost to enter the fair and not purchase an apple. Or we could say and purchase 0 apples. Okay, so just writing equations, nothing too terrible right there. Okay, so our learning targets for today are to talk about how are we going to determine the average rates of changes for sequences and functions. All right, so sequences that we're going to see in a table as a function if we see it in a graph, including linear, quadratic, and other types of functions, and then determine the change in the average rates of change, so change of change for those same types of functions. So let's talk about what we already know. Okay, we've been working on average rate of change. What do we know that's the same thing as? That's the same thing as slope, okay? That's the same thing as slope. It's our change in y over our change in x, or f of b minus f of a over b minus a, okay? So a and b are 2 points, our x values on the graph. Okay, so average rate of change. And then what did we say was our instantaneous rate of change? It's the slope of the tangent line at one point on a graph. So they're both slope. All right, so slope of our tangent line. All right, so let's see one that's got some interesting values in it. Okay. Let's look at this first example. Because we're given that the volume of air in a spherical balloon varies with the balloon's radius according to the volume formula, V of R equals 4/3 pi r cubed. Use function notation to represent the average rate of change of the balloon's volume in terms of its radius as the radius increases from 2 to 5 inches, and then include units in your answer. Take a second, use your calculator, okay, and let's get that value. Bless you. Allergic to math.
Had too much of it today.
What's your favorite fidget in the box? These, yeah, these are most people's favorites. I have a box of Legos. I've been meaning to get some of my Legos out and just throw them in the basket and see what people come up with. But then I'm afraid I'll have Legos everywhere, you know. If you knew my third block last semester, we would not have Legos. God love them. Most of them graduated though, so that's good news. Alrighty, so let's take a look at this one. So we've got our volume formula up there, 4/3 power cubed, and we're looking to do V at 5 minus V at 2 over 5 minus 2. So basically we're just plugging things in. 4/3, you've got that pi button. It's good to use it. Minus 4/3 pi, and then 2 cubed all over 3. Did we get 163.363? Okay, now let's talk about units. We're doing volume, all right? Our radius was measured in inches, and so what kind of units would we use for volume? A little geometry. Do what? Cubic, okay? We use cubic because how many dimensions is volume? 3. Okay, it's 3-dimensional. We can actually pour something into it. So inches cubed, remember it's a rate of change. And let's see, our radius was measured in inches. So this is a weird unit, but it is inches cubed per inch. Okay, that does not reduce to inches squared. All right, it's a rate of change. So we use the volume units over the radius units. Inches cubed per inch. You'll get to see a lot of that in calculus. Let me look at all that good stuff. Okay. So now let's take this rate of change question. Let's just kind of adapt it a little bit and talk about what we could do. All right, so let's look at another example. So flip that on over. Okay. And it says that Juan's traveling on a curvy road to attend his friend's wedding. After driving for 90 minutes, approximately 3/2 of an hour, on the curvy road, Juan's odometer indicated he had traveled 60 miles. What was his average speed over that 60-mile stretch of road? Let's include our units. How might we go about doing that one? A little different. We can't multiply. That's a good thought, though. Okay? Remember, when we do rate of change, we're going to divide. All right? We always divide. Total accumulated change over accumulated change, right? Change over change. So let's see what we're talking about. If we want to know his average speed, we're talking about the change in his distance divided by the change in his time, okay? It wasn't given to me in the form of a function. It wasn't given to me in terms of ordered pairs. They just gave me some value. What was the total distance he had traveled when he looked at his odometer? 60, okay? And it wants me to do, let's see, let's use hours because we don't really talk about miles per minute, okay? And then what was his total time that he had traveled?
90.
Yeah, 90 minutes. Let's do hours, so 3/2, okay? So we want to take 60 and divide by 3/2, okay? When I divide, I'm really multiplying with fractions. So this would give me 40, and what would be my units? Miles per hour, okay? So just a little different way that they could ask me a rate of change question, all right? We just got to remember it's that accumulated change in something over change in something. Change in your dependent variable over change in your independent variable. Right. Now, they take that question a little bit farther in part 2, and it says, as Juan is driving, he notices that his friend's wedding begins in 15 minutes, which happens to be a quarter of an hour. According to his navigation system, he has 7 more miles of driving on the curvy road to get to the destination. All right? He must not have Waze, which tells me what time I'm going to get there. All right, just a thought. So we're going to use the average rate of change of 40 miles per hour that we already computed to predict if he's going to make it on time to the wedding. Okay, so this time we know his rate. Okay, he's going 40 miles per hour. How much more distance or how much more time does he say that, or when does the wedding begin? In how many more minutes? 15, which is how much of an hour? A fourth. Okay. So if I take 40 miles per hour times 1/4 of an hour, how many miles do I have left? 10 miles, okay? So it says I can go 10 miles in 15 minutes, all right? How many more miles does he have to drive? 7. So is he going to be on time? Yeah, he'll be on time. He'll be on time. Right. So just a little few more rate of change things. How are rates of change different between a linear and a quadratic function? Got a linear function versus a quadratic function. What's different about their rates of change? Yeah, the linear function has a constant rate of change. Okay, it has a constant slope. If it's a line, it changes consistently, all right, by the same slope every time. If it's a quadratic, if it's a parabola, that's not going to happen. All right, the slopes are going to be different. In fact, we could actually look at some of those tangent slopes and see real easily, yeah, it's negative, it's 0, it's positive. Okay, so the slope changes in a quadratic. Okay, so I've got a table here, all right, for some function, and we want to explain why it's not linear. Okay, what's something we could test to see if it was linear? Yeah, let's do all the rates of change, all right? If it's linear, they should all be the same, okay? So we're going to do these average rates of change between every ordered pair, okay? If it's linear, I should get the same thing every time, right? So I'm going to start with the first one, so change in my y value, so 7 minus 4 over 2 minus 1, which gives me 3 over 1, or just 3. Okay, so that's the first set. And then we'll do the second set. And our average rate of change is going to be 10 minus 7 over 4 minus 2. And I get 3 over 2, okay? We can stop there, but if we did it again, we would find that the rate of change is not the same, okay? The rate of change. So why is it not linear? The average rates of change are not constant. Okay, so you're basically just taking those ordered pairs and doing slope over and over and over. Okay, if it's linear, we should get the same thing every time. I'll do that last one just so we have it in our notes. 13 minus 10 over 8 minus 4 gives me 3 over 4. Okay, just showing you where it comes from. The average rates of change are not constant. Okay, so we're going to do a little investigation here for just a second. Let you guys use your calculator and get some values and plug some things in, and we're going to talk about what happens with a quadratic. All right, see if we can draw some conclusions. All right, So there's a lot of words here. Let me just kind of analyze it for you. It says we're going to analyze average rates of change over equal length intervals. Answer the questions below to help analyze. And here's our function. So they actually give me the entirety of the function so I can see it. I got it right here, y'all. Okay, so I'm going to use it because I think it's going to ask me to get some ordered pairs here in just a second. It says the graph indicates 8 chosen points separated by an equal spacing of 0.6. Okay, so in other words, every point that it gives me is a distance of 0.6, change of 0.6 on the x's. Okay, so the x's are changing by 0.6. With one of the points labeled correctly, label the remaining 7 x values along the outside. So if this is 1.8, if I go backwards 0.6, what's this x value going to be? Yep. Okay, and then if I go forward 2.4, etc. Okay, so these are my x values that it's given me. Okay, so you can get the x values that you need all the way around. You're just going to add 0.6 every time. Okay. Then it tells you to enter the function into your graphing calculator, calculate the average rate of change of W over one of the indicated intervals, and report your results as a decimal value in the table below. Connect the points in the graph to form the secant line. Secant is just where you connect 2 dots on a graph. Okay, so with a straight line. Use a highlighter to show the secant lines where the graph is decreasing and another color to show where it's increasing, and then continue finding the average rates of change and coordinates of each point. Give the coordinates of the vertex of the graph. So it just gives you lots of instructions, okay? There's a lot there, all right? So you're going to fill in your chart here, your y values, you list your points, do your average rate of change, and then what do you think this last line talks about? Any idea? What does that little triangle symbol mean? Anybody know? It means change, okay? So after we find our average rates of change, we're just going to subtract them to get the change in the change, all right? And that's what goes in that bottom row, all right? So this is going to take you a minute to do, all right, because it's asking you to do a bunch of stuff, all right? So take a second with your table groups and let's get all that stuff on this information, and we're going to see if we can figure out what's going on, okay? Ready, go. So all your instructions are there on the side. Oh, 99-cent corn dog day at Sonic. Just got an alert. You're a corn dog fan. I like fair food. You can deep fry it, stick a stick in it, it's good. Oreos. Yes. Well, if you get 2 and they don't match, you can stop. Because if it's linear, they should all match.
But if they they don't,
And now we'll keep going until you touch yours true for all. Yes. Let's see, let's see.
I like different frosty.
Yep.
I like it. I just like both of them.
And now you can type your next. You're welcome.
Well, neither of them hurt my stomach. It's just, I like the taste of buffalo wild wings, like buffalo. And then yes. Yes. How to find the Y's.
Okay, we're gonna take these numbers that you've got and we're gonna plug them into that equation.
Oh, that was just, yeah. Yep, thank you.
You're welcome.
You said that was both, and then you didn't tell me.
You sure?
Oh, I forgot my big equation up there.
Y'all good if I run down to my car and grab something real fast? Okay, I'll stay here. It's snacks, but that's okay. I know. Yeah, we're good for a second. Well, I'll run down here real fast. You.
Yeah, I like myself too. I like Izzy, but lately, well, she's on my team. But lately, they have not been focusing on practice. And it's like really my nerves. I'm so supposed to be tired, are you? How?
The girl, her name's Mary. She's stalking me. It's like, oh, that's awkward. That's cringe, right?
Yeah. Not there?
She don't like my nerves. But I like prayer class. She's so much.
I'm always at home to practice it with y'all. But that's because I'm like, I don't know, it's just me, I don't know. I'm trying to improve and I just, cause if y'all never have anybody there,
No.
I end up just making it even for y'all.
I need to look at it. What's that mother supposed to be at? Wait.
High thirty. Yeah, it starts at 2. I had to do it like 6 times.
It's gonna be what? It is, is that what you said?
Thinking about it. No, I'm gonna get my dress altered. So I'm not gonna eat before that because I won't load it until I get the dress on. It's hard to zip up a dress. The blue one.
Oh, yeah, I apologize. We've been here as long as I do, you get first bid of carpet.
That's the game I got a yellow hair.
I think Sawyer got one too.
I don't remember. I just remember me getting it. Which was not necessary. I got it for retaliating, but this girl was shooting in the back that the ref was calling. I'm sorry. I can't. No, this girl the whole game, her hands are like in my back. And like, okay, if he's not gonna say anything, I'm just fixing to go push her because I just get off of me. Like, she was literally, I was trying to move back and she was literally pushing me and keeping me forward.
Don't worry about that one, it'll be
That's like the first yellow card I've gotten in a while.
I don't know how y'all run that much. Like, when I go and watch soccer, I'm just tired watching y'all. I mean, I've not run since 1992, I can just be honest. That's when I blew my knee out the last time. And he was like, don't run ever again. Done. Deal.
I'll take it.
No argument.
The condition plus the word not is harder than the actual soccer game.
Yeah.
I mean, I feel like that's pretty obvious.
I mean, y'all, I can't walk and chew gum at the same time. So me trying to kick a ball, run, no. It would be a disaster.
Is it between?
Yes, between those 2 points, you're just going to connect them.
For all of them?
Mm-hmm. Just connect the dots.
Okay. And then, what is this?
That's what you got right here. That's your average rate of change.
Okay, and then how did you find the changes?
You're just going to subtract those two numbers and put it right there. Subtract those two and put it right there.
Oh yeah, that was in the morning, what we did in the morning.
So I got a thing that you're going on a field trip January 31st. With Miss Zilms, are you going? Miss Zilms? Zilms, the career coach. Yeah, there's like a list of like 50 names. You you don't know anything about it? Okay, well maybe, hey, you might be going on a field trip January 31st. She's over in the CTE building by Mr. Anderson's office. Okay. A lot of times she just takes classes and they go, oh, here's one. The 7th, yep. Oh, no. Okay, my husband's driving y'all's bus. We didn't know who it was. We knew you were all were going over there, so. Okay, there you go. Thank you, ma'am. Y'all going to Vol State, I think. I'm not sure.
She's just like, she's just started her hair and she always wears it.
You can tell her you love pre-calculus so much you'd rather come in here.
Oh, is it? It might be.
We ain't got to talk crazy, do we?
I really.
You know what else I don't like is Eddie.
I forgot about it. I like
I do not like him.
Is there an extra box at the end?
Yes. Yes.
Yeah.
Okay, so you're going to take this number and subtract it. It goes right there.
which way we put it. So do you want
Always do
This-
right minus left. Yep.
Oh,
Okay, yeah, I did do it right. So if it's subtracting, it'd be negative 0.9 plus 1.5.
For
'Cause
this
a
one,
negative
you
minus
do
a
right
negative.
minus left. So do this one minus that one. So
Oh.
negative 1.5 minus negative 0.9.
So
Yeah, same with that one. Yep.
0.6,
Yep.
just for all of them.
Yep, and this one.
Oh. Would that be negative 0.6?
Yep.
Oh, they're all supposed to be negative
Yep.
0.6. Yeah, I see that now. Thank you.
You're welcome. Okay, so I got my ordered pairs. Is that, y'all double check me, make sure that's right. Sometimes I write things down crazy. Okay, when I'm doing it ahead of time. Okay, is that what you got for your X and Y values? Those look good? Okay. All right, so then we go about finding our slopes. All right. So I would take 2.78 minus 1.88 divided by 1.8 minus 1.2. And here's what I got. I got 1.5, 0.9, 0.3, negative 0.3, negative 0.9, negative 1.5, and negative 2.1. Okay? So those values represent, up here where it talks about m equals, those are the slopes of our secant lines. Okay? So if we connected the dots, all right, between all of our points, those are their corresponding slopes. Okay. Alrighty. Then it asked me, where is this function increasing or decreasing? So I'm going to switch to my highlighter. Okay. Which side of the graph are we increasing on? Yeah, the left-hand side. So we're increasing here. So I'm just going to put increasing so I know that's what I was doing. And then let me change the size of that bad boy. And then I'm decreasing over here. Okay, so I'm decreasing. Nope, not that. There we go. Okay, now how does that correspond to what we already know about rates of change and where things increase and decrease? Does it coincide? Does it make sense? It's what we've already done. What's true about our rates of change when the function increases? They're positive, okay? And so if we look, all of our rates of change on that left-hand side are positive. And then if we look on the right-hand side, all of those rates of change are negative, okay? Based on the rates of change and the fact that we have a picture, is it obvious that this is not a linear function? Sure, okay? We can tell that's not a line, all right? But now I want to talk about that change in the rates of change, okay? So I want to actually look at this chart right here where we subtract, okay? Where I do 0.9 minus 1.5, I get negative 0.6. 0.3 minus 0.9, I get negative 0.6. Negative 0.3 minus 0.3, negative 0.6. What happened for every one of these? They're all negative 0.6 when I do that rate of change, okay? That is referred to as what we call the second difference, okay? So this is a name. It's called the second difference. All right? And it is the change in the average rate of change, okay? So we call it the second difference. When that second difference is constant, all right? So when the change in the rate of change is constant, it is always a quadratic function. Okay, always quadratic. What makes something quadratic? If we think about the equation itself, what makes an equation quadratic? X is to a power of 2. So when it is a second difference, it is a second degree equation. Okay, so when we have a second difference that's constant, it is a second degree equation. It's just a really cool thing. Okay, so that being said, let's flip the page over and see if we can draw some more conclusions. Okay. So if a second difference gives me a quadratic, how many changes would I need to find for a cubic function? 3, our third difference. Okay. Change in the change of the rate of change. Like it just goes on and on and on, right? What about for a quartic? That's a word you may not have heard before, but I know what a quartic is. 4, yep. It's a 4th degree equation, so it would take the 4th difference. Okay. The 4th difference for a 4th degree equation. If it was a 6th degree equation, we'd have to do the average rate of change and then subtract 5 more times, and then I'd get a constant. Okay. So it works. Now that's exhausting, and we're not going to do that. Okay. 6 times. That'd be crazy. Right. That's why we have regressions. Okay. But that's how it works. All right, which is kind of nice. Remember, common difference is just the change in the average rate of change. Okay, and we're going to keep doing it until it's constant. Actually, let's not say keep doing it. Let's say keep finding the change. Let's say that. I like that better. Oops, spell fell. Okay. All righty. So let's take a look at an example, and then we're going to do several more examples, and we're going to be done for the day. Okay? It's like just talking about this rate of change and how rates of change are moving. Okay? So it says, let's consider a graph that represents a car's distance in feet north of a stop sign. So the car's up here, stop sign's down here. In relation to the number of seconds since the car began to move. How does the car's distance north of the stop sign vary with the number of seconds since the car began moving? All right. So is the car speeding up, slowing down, or moving at a constant? Did y'all see that? Bless. Constant. A rate of change, and how do we know? Okay, how do we know? So this is what they're asking me. You want to talk about the values in the table to explain how the car's moving. All right. So let's look first at the picture itself. Okay. Is it moving at a constant rate of change? No. Why not? It's not linear. Okay. So it's not moving at a constant rate of change because it's not linear. Okay. Point blank and period. They gave me the picture. We know. Okay. So now what it's asking me to do is to think about the change in each variable so we can talk about the slopes. Okay. So from 0 to 2, it changed 2. From 4 to 2, it changed 2. From 6 to 4, it changed 2. From 8 to 6, it changed 2. Okay. So the time is all changing by the same value. Okay. Now let's do the change in the y's. Okay, this is not average rate of change, just the change in the y's. 4 minus 0 gives me 4. 16 minus 4 gives me 12. 36 minus 16 gives me 20. And 64 minus 36 gives me 28. Okay, so now let's take those values and get the rate of change. Okay, let's get the rate of change. So 4 over 2 would give me 2 feet per second. 12 over 2 would give me 6 feet per second. 20 over 2 would give me 10 feet per second. 28 over 2 would give me 14 feet per second. Okay. So now let's see if we can answer this question. Do we think the car is speeding up or slowing down? Speeding up. Why do you think it's speeding up? Yeah, the rate of change, its speed is increasing, okay? So we would say that it is speeding up, okay? Because the rate of change is increasing. Okay. All right. So now, let's see if we can figure out a little bit about what kind of function we think maybe this is. Okay. It didn't ask me specifically, but we know it's not linear. All right. If we think about doing the change again, all right, so just of that rate of change, 6 minus 2 would give me what, bless you? 4. 10 minus 6 would give me 4. 14 minus 10 would give me 4. Okay, so the rate of change and then that difference, that was our second difference. This is actually a quadratic function. Right? It's a quadratic function. Okay. Now, here's some words that they will say about it, which I think are kind of interesting. All right. A quadratic function increases, the rate of change increases linearly over equal intervals of the domain. And that's a lot of words. Okay. A lot of big math words to say that this rate of change increased by a constant amount every time, okay? And so I want to give you that phrasing just so you can see it and have it in your notes. We would say that this function, the rate of change, increases linearly over equal intervals of the domain. All right, I don't want you hyper focused on that phrasing right now, but we're going to see that those words used a lot. So I just want to kind of put it in your brain somewhere in the cobwebs. Okay. So our rate of change increases linearly. It went up a constant amount over equal intervals of the domain. Now, if we look at that graph, is it concave up or concave down? It's concave up, all right? We can see by looking at it that it's concave up. And so when we think about the average rate of change, okay, it tells me that the average rate of change over equal length input value intervals, in other words, if my x changes by the same amount, okay, then it is increasing for all small length intervals. And we know that if the rate of change increases, then we have concave up, okay? And likewise, concave down, if it's decreasing the rate of change over equal length input, okay? We can't guarantee that if my x's change by different values, okay? So if x changes by 2, then it changes by 6, and then it changes by 2 again, we can't guarantee, all right, the concavity. It has to be equal length x's, all right? So let's look at about 4 more examples, and then I'm done for the day. Yay. Okay. I'll give y'all time to work on your practice a little bit. Make sure you feel good about it. Okay, so let's jump in here and look at these. Okay, fat fingers. All right. So selected values of various functions are given in the tables below. Determine if these functions could be linear, quadratic, or neither. Okay, so let's do one together, and then we'll go from there. Okay. So what I need to do is I've got to first find the average rate of change. All right. So I like to just kind of do some quick math. These are all changing by 2. Okay. okay? And then I go to the y side. That's going to give me a difference of 2, a difference of 1, a difference of 0, okay? And the first column I'm going to start with is my average rate of change. Okay, so I'm going to do those ratios. All right, 2 over 2 would give me 1. 1 over 2 would give me 1/2. 0 over 2 would give me 0. All right, so is it linear? No. Okay, those numbers don't match. It's not linear. All right, but what we want to do now is that second difference. Okay, so I'll just put a difference, D-I-F-F. All right, let's do our difference between these y values. Okay, second minus first. So 1/2 minus 1 gives me -1/2. 0 minus 1/2 gives me -1/2. When it's equal, okay, I've done how many calculations, how many columns? 2, so it is a quadratic function, okay? Now, one of the things that we've got to get used to doing is writing reasons, all right? And here's what we're going to say, okay? We would say that the average rates of change over equal intervals of x decrease at a constant rate. Right. Now, I'm not going to ask you to write that in your practice or anything like that. Like I said, I just want us to start thinking about those words. All right? Y'all try the second one. Okay. All right, let's see how we did. Let's do our calculation. See, that's going to give me a 1, a 3, and a 5. 1, a 3, and a 5. Now, when we do the average rate of change, what do you notice about all of them? They're the same, right? You should get 1, 1, and 1. All right? So we would think that it's possibly or probably what? Linear. What's the only problem? Anybody see anything? Is the change in your x values constant? No. Okay? So this is what we say. Okay? We say that it could be linear. Right? Could be linear. We just don't have enough information to know. Okay? We could be linear. Average rates of change are equal, but not over equal intervals of x. Okay, so we would say that it could be linear. All right, we got a constant average rate of change, but they're not over equal length intervals of x. Okay, and that's an important characteristic that we're going to always look for. Okay. Question about that? Okay. All right. The next two examples ask us to talk about concavity. Is it concave up, concave down, or neither? Okay, concave up, concave down, or neither. All right. The same things apply. We're going to start with that average rate of change. If it's concave up, those average rates of change should increase. If it's concave down, they should decrease. Okay? And then if you get the same average rate of change, it would be neither, because you got to increase or decrease to have concavity. Okay? So let's look at one together. Let's look at this first one together. We're going to do the same process. All right? 1.1 minus 1 is 0.1. 1.2 minus 1.1 is 0.1. Okay, so my x's are in the clear. They all changed by the same amount, which I wanted to be sure happened. Okay, let's go through and do our y's. 4 minus 1 is 3, 7 minus 4 is 3, 10 minus 7 is 3. And so when we do our average rate of change, 3 divided by 0.1, well, it's not 30. Okay, equals 30, and that should happen every time. Okay. So we got a constant average rate of change. It's not increasing, it's not decreasing, so does it have concavity? No. Okay, so we would say it's neither, all right, because the rate of change is constant. Okay, y'all try that last one. I need more Germix. Got it. I may have some in my cabinet. I'll look just a second. Some of it had gotten old and it was stinky and it had to go. Okay. Is that what you got for your average rates of change?
Yes.
Okay. So they're obviously not constant, so we've got some kind of concavity, all right? Are those values increasing or decreasing? Increasing. It's weird when it's negative, right? We increase when we get less negative. We decrease when we get more negative, okay? So this is increasing. So we would say this is concave up, right? Because the rates of change are increasing. All right, I picked that one on purpose because for some reason those negatives get our brains all backwards. All right. So we just have to be careful. If we get less negative, think about the number line, you're moving more towards the positive side, so you're increasing to the right. Okay. Questions over what we did today? Really, we're just doing rate of change and looking at that table, figuring out, do we have a linear function, a quadratic? Are we concave up, concave down? Okay, so I feel like that all kind of plays really well together with what we did the first two sections, so that's why I put it all in the same quiz together, okay? All right, so your lesson practice, okay? So on worksheet B for 1.3, these are the problems I recommend you look at. 1, 3, 7, 9, 12, 16, and 18. You are welcome to do all of them. The answer key has all of them, okay? So if you do one and you get it wrong, you're like, God, how did I miss that one? Do another one, okay? There's extra, right? I really, really, really recommend that you look at the AP lesson practice, okay? That's the second sheet that's there, okay? Those are pulled from AP Classroom. They're written like the questions you will see on the AP exam, all right? They are multiple choice, which is good. So I think it's good for you to see how they're going to word it and then how they're going to try to trick you, all right? So we want to see that from the get-go. And there are all 4 of those I'd like for you to look at, 1 through 4, okay? Now, this is something new we've not done just because of time. Today you have a wrap-up, all right? It's on Google Classroom. You get a point a day for doing it, okay? So if you need to access your phone to get to your Google Classroom, that's fine. But do it on your iPad. So if you go to Google Classroom, it'll be one of the last links, all right? And it says wrap up. You're going to click on it, okay? It's usually one question. It's multiple choice, 9 times out of 10, okay? And I just want to see how you do, okay? It's okay if you get it wrong, all right? I just want to see how you processed what I talked about today, all right? So I'd like it to be your work, okay? So just do the best you can, all right? And do that. And then you've got the rest of the class time to work on your practice, okay? So be sure and get that wrap-up done so you get that point for today. I know it doesn't sound like a lot, but we'll be grateful for all the points we can get at some point, okay? Just saying.